let's begin with a sample problem that you should know how to do, transitioned into a concept that maybe we know a little bit less about. So let's imagine real quick that here is the side of a ship, okay, and that they have created a temporary plank on this particular ship, all right? And there is a victim, or you can give them a name. I don't care over here. That's Jeremy or Denise or Kylie or Tyler or Tyra. I don't know. Anyway, and they're on the very end. We're going to say that the plank is 8 feet in width. Okay. It is sitting, by the way, this is the deck of the ship, and it is in the absolute center of that right here. And then over on this side, we have a pirate who, my apologies for not being very good drawer. Here's their foot. They're very flexible. All right, so here they are. Is like a sword. Okay, and then he actually lost half of it in the last battle. All right, this foot is, let's go, about 2.5 feet from the center. And we're going to say our victim over there on the side is 150 pounds. Okay, the question at play right now is, what is the force? What is the force that the pirate's foot has to push with in order to keep that plank from rotating and falling into the ocean and keep that victim where they are? Okay?
It's more than 2.
I'll let you work it out.
Is it less than 2?
I will let you work it out.
Sounds like you have to work it.
It does sound like you have to work it out. All right, for people online, I would suggest that you do the exact same thing, but I will pause right now, letting them work so you don't have to listen to a bunch of silence, and I will restart here in just a second. Once it's done, try to do it yourself. All right, I've done a little bit of work on here. You can see some conversions up here, but we haven't done any actual calculations. We converted 150 pounds over to 670 newtons. We converted 8 feet up top to 2.44 meters, and the distance of 2.5 feet on the bottom to 0.76 meters. And I was just sharing with them, and I'll show you actually do not need to do the conversions on this particular front. Okay, I'll show you how that works here in just a second. So what you'll see here is that we technically know one force out of 4 of them. Yes? Okay, we know that force right over there, and we are looking for this force right here. So these two forces, we don't know either of them. Okay, that being said, what thing can we do with torque in order to make it that they're non-issue? So one step in front of me. Before that, what do you do in order to make that the case? You place your fulcrum right here. By placing your fulcrum there. Now let me be really clear, because this is a mistake that a lot of people have. Does that cancel the force of gravity or normal? No, the forces never cancel. They are still there just like they always have been. What does it cancel? The torque created by those two individual forces, yes. So now I can come over here and I can sum the torques and say that's equal to 0 based on my picture. Let's see if I can squeeze this down here real quick so we have both up here. What are the sum of torques in this situation? Let's go left to right and start with pirate. What is that? Positive or negative? That would be positive. Torque pirate. Okay, and of course both of these two are 0 because there is no lever arm, so I just typically choose not to draw them. If you do tend to draw them, that's fine. Just immediately cancel them out so they don't like mess you up while doing this. And then finally, torque of victim in this case would be positive or negative? Negative, which of course you can immediately get because there's no way it can't be negative given that we believe that it should be canceling to 0. Of course, if they were both positive, then it cannot equal 0. We'll talk about that a little bit later. Of course, your work here gets that the torque of pirate has to equal the torque of victim. Kind of makes sense. And what's my equation? Well, it should be lever arm of pirate times force of pirate. What is the angle on the pirate? It should be 90 degrees right there. Very good. So I'm just going to multiply by 1 over here and then equal to lever arm of victim times force of victim. And what's the angle on the victim? 90 again. Thank you. Very good. All right, now to find force of pirate is just going to be now. Of course, you can do algebra however you so choose, but some organization here can make your life a little bit easier in understanding. What I regularly like to do in a problem like this is combine the variables sort of together in an organized fashion. Meaning, I'm going to take lever arm of victim divided by lever arm of pirate times force of victim. And right here, that tells me something specific about the lever arms. Did I need to convert to meters? Why not? Yeah, and more importantly, well, no, same importance, the ratio between whether or not they're in feet and the ratio between whether or not they're in meters should be the exact same amount. Now, I didn't stop anybody making that conversion because if you've already done it, do not erase it. You will absolutely use it later. Please leave it alone. Just leave it where it's at. But technically, 2.5 divided by 4 is going to be the exact same thing. I said that backwards. 4 divided by 2.5. Okay, it's the same thing as 1.22 divided by 0.76. It's going to get you the exact same ratio in that case. Also on that front, here's another important thing. Technically, I also don't have to convert pounds to newtons either usually. Okay, I could leave this in pounds over here and I could say, all right, doing some work real quick, this ratio is 4 divided by 2.5, okay, times 150 pounds. And what I get is that the pirate has to put out a force of 240 pounds. Now, if the problem then asked me what that was in newtons, I could just convert that at the very end by multiplying by 4.45, and you would end up with 1,068, just the same as you did if you converted all meters and newtons from the very beginning. Make sense? Cool beans. All right. We are going to move on now to the new thing. Now, as we continue in this class, I want you to understand something. I've said it a few times throughout here, but I want to make sure that as we continue and do particular things later on, that this hits in the right way. This class is designed to help you do better in college, in school, in whatever the heck it is you want to do, not just in physics. One of the most valuable things that you can learn to do is read the book. If you are not currently reading the book for this class and are unhappy with how this class is going as far as your knowledge is concerned, I have one major piece of advice for you. Now, I understand you might come back with me, Spain, now I don't have time. And I'm going to tell you how this usually goes down for absolutely every person who I give this advice to. What happens is they go, I don't have enough time because I'm always working on all of your homework. What I challenge them with is a couple of things. Number one, I tell you exactly what reading to do on every single day, and usually that's about a page and a half, which means at max, usually it takes you somewhere between about 5 to 10 minutes in an advisory that you probably didn't have anything to do with anyway. That being said, when you do that reading, 9 times out of 10, your homework goes infinitely faster because you know exactly what's going on in it and what it's trying to describe, and the textbook knocks out like 90 different problems that you didn't know that you had before you actually have them, and it goes way, way faster. That being said, even if it doesn't, I'll tell you the truth. Every single college student would tell you the same thing I'm going to tell you, and that is this. In any class, I don't care science or otherwise, the reading is often not required. Meaning, no professor is going to stand up in front and say, read the textbook oftentimes, unless, of course, it's an English class. Okay? But what you're going to find is when you actually decide to do that is when you actually start learning the process. Last thing, advice I'll give you on this, and then I'll move on to what we're going to do today because it directly relates, is this. In high school, a teacher typically takes on kind of a moniker of this. I'm going to do 80% of the teaching and try to organize their thoughts about 80% of it, and 20% of it is probably going to come from the homework that they do and the work they do on their own. Okay? Just as a heads up, most college professors have those two ratios flipped. I'm going to do about 20% of the work, and 80% of the work is going to come from them. I was literally having a conversation with a woman who's about, she's a little younger than me, but adult definitely, and she's in college right now, and she regularly kind of complains slash talks about the the innocent children coming out of high school, and this like misguided view of like complaints that she always hears behind them. And it's like, I don't get this class, I don't get this class. And what it really usually boils down to is that they have not yet taken responsibility upon themselves to actually do that 80% of learning. Know that that will switch. You better get good at reading the book. So here's what we are going to do today to start to encourage that particular behavior. Instead of me teaching you the concept today, I am going to give you the concept, and what you're going to do then is you're going to explain it back to me in about 15 minutes. And then, of course, I will make sure that you're good by filling in all of the blanks of stuff that you may or may not have missed on that particular front. So you don't worry about anything. You're still going to get all the information that you need to. This topic takes. But you can use the internet, you can use your textbook, okay? You can use whatever the heck it is that you want. No, it's not just an easy definition equation. Sometimes people do that. They go online, they read the definitions, like, oh, let's phone it in for the rest of the time. Not quite so easy. Here it is. Concept is moment of inertia. Go look up in about 15 minutes. Please use your group. You're meant to work together on this. Alyssa, if you want to transfer over here, obviously in this particular case, I would highly suggest it. Okay, use your group. Everybody look in different areas. What is moment of inertia? Couple of highlights before we get going on this. Let me help you real quick. Inertia is inertia. It's the same inertia that we talked about previously. And the word moment, okay, is an engineering word for the word torque. If you go to an engineering class in college, they don't use the word torque often. They would say moments. So instead of summing torques, they sell moments. So moment of inertia essentially translates to the torque of inertia. Discuss. Those of you guys people online, once again, I'm going to pause and we'll bring you back together once we're talking about it. Oops, my bad. Forgot to hit play. All right. I'll hit the highlights here in just a second in the review in just a second for anybody online. My apologies. I knew that it was going to happen. All right. This equation right here gives you your equation for moment of inertias. Okay. We will practice with all of these, no freaking out, but you can kind of see some of them right now. Like I said earlier, this is mr squared. This would be rod about its center, and it's pretty close to mr squared. It's just there is some fraction right here. By the way, what variable letter is used for moment of inertia? I is what's typically used in this particular case. Okay, you see, like, for example, the cylinder I talked about earlier. Watch here. The cylinder, this is going to be mr squared, right? R being the distance from orbit. But what if the cylinder starts spinning like this? Is all of the mass at the radius? Which is why, in this case, you would use solid cylinder or disk around a symmetrical axis in this particular case, okay? So, again, let me be very clear. If all the mass is out at a radius, it's mr squared. Simply put, if the object is orbiting, kind of, you imagine that dotted line. If it's orbiting around that dotted line, always mr squared, okay? If the dotted line runs through the middle of it and it's orbiting, or it's rotating around itself, boom, you go here, okay? So Sally, for example, you'll notice the picture's not super helpful. We have solid sphere and thin spherical shell. Best way to do this, by the way, is to use it in most sport balls. Okay, Sally would be which one probably? Solid. Solid, correct. The counter to that, of course, would be tennis ball. Would be thin spherical shell, as would basketball. A simple thing to look at, basically, if it's filled with air, it's probably thin spherical shell, right? If it's like a baseball, it would be solid sphere all the way through and through. If you ever don't know out of ignorance, right? If your ignorance of sport balls, whatever, is keeping you from the knowledge of which one of these is, please feel free to ask. I have no problem. I'm not going to tell you which one to use, but I will tell you if it's full all the way through. If you don't know this, in a bowling ball and in a baseball, it is actually not the same material all the way through, which arguably does affect its moment of inertia. We will not worry about anything like that. And here we will assume that it is a solid, same material all the way through that particular object. You might see thin hoop around a symmetrical axis. Well, that would be like, where's my, here we are. Hey, I got a wheel right here that I'm spinning around just in the normal way, people online. Okay, we're not going to worry about this stuff in the middle. We're going to say that most of the mass comes from the tire itself out here. Now, in this particular way, is all of the mass at the radius of the tire, for the most part? Yes, which is why that makes sense that that is, in fact, straight up mr squared, right? Versus the opposite, is it spinning around its diameter, like this right here, is all of it, my bad, okay, is all of its mass out at this radius? Nope, which is why it makes sense that now you have a fraction, in that case, 1/2 mr squared. And like you said, if you're curious where those fractions come from, go do a physics calculus, but for our purposes, this is the only table we are going to use. You should find all of them on, it will either be mr squared or it will be this guy right here. Yes?
What if you're hula hooping?
If you're hula hooping, excellent question. Now, it's a little bit tricky in that regard because obviously the axis is moving, but if we were kind of looking at the center, we would probably use that one. It's just kind of all at some rotation from that particular guy right there. Questions, concerns so far? So let's review real quick, especially for people online who missed the first part of this. What is moment of inertia at its heart?
The resistance.
Resistance to rotation, and is the analog of, it works the same thing as regular inertia, just for rotation, right? Simply put, what is moment of inertia? How do you change your moment of inertia?
Changing how much mass is far.
Take mass, put it further away. So why does the person on the tightrope carry the large stick?
Put a lot of mass very far, so they don't accelerate.
There it is. There it is. Sort of. Like there's two pieces of that. One, they don't want to carry a ton of mass, but you'll notice from this equation, what is arguably better for inertia? Mass or radius? Radius because of that squared. So yes, more mass further away does it, but actually arguably if you can double length and cut mass in half, your moment of inertia still goes up because length is more important than mass in that case. So you can hold a very thin object as long as it's out as really far away, that jacks up your moment of inertia, making it a lot harder to spin in that particular case. That being said, all of you do this if you have to balance in a much easier, smaller capacity. What do you do if you have to walk across a balance? You put your arms out as far as you possibly can, and that's because it increases your moment of inertia. Mathematically, as we said, if all of the mass is at the same radius when you're going around, think like essentially kind of orbit. It's not exactly orbit, but like just like a stick at some distance from me in this case. I straight up use mr squared, always, always, always. But if the object starts spinning around itself, in this particular case, you would use thin rod about the center. In this case, you would use rod about its end. And you can see mathematically what we said earlier. Which one's harder to spin? This one or the second one? The second one. And how do you see that mathematically up here? This has a larger fraction than this does. So at the same mass and the same length, this one on the bottom has a larger moment of inertia. How we doing? All right. Now let's use this to go back to our problem and calculate a couple of things. Man, I'm not going to finish early. I don't know where I lost my time. I apologize. Okay, so we're going to go back to this example and ask this question real quick. What would happen if the pirate takes his foot off the bridge?
It tilts.
Apparently, by the way, his foot, for the sake of time right here, his leg got blown off by a cannonball. Okay, the victim is going to fall, or the bridge is going to rotate. Exactly, because sum of torques is not equal to 0 anymore. Do this for me first. Let's go ahead and assume that the mass of the bridge, which you the plank, which you now do need, is 18 kilograms. Go ahead and calculate the moment of inertia of the plank now. Because where does this thing going to rotate around? It's going to rotate around the center. So what should you be using here? 18 kilograms, yes. So I'm going to go I is equal to 112 mass. Now, be a little bit careful with these guys over here. Okay, the pictures don't do great for the equations. All of the 6 on the left side, you'll know, are using R. Those are radiuses. But you come over here and you see it say R and define it differently. That's not radius in this case. That is, in fact, and this is why there's an L here, that is the entire length of the rod, right? So you might be pulled into like, oh, radius, so I should use 4 feet or 1.22 meters. No, these equations over here are, in fact, defined by the entire length of the object, not just an air quotes radius on that guy right there. So what should L be? Let's do this. What should, you got it. Okay, what should M be then? 18 kilograms times 2.44 meters. Someone calculate that for me real quick. And of course that is squared.
53.58.
It seems too big, if I remember correctly. Am I wrong? Maybe I'm wrong.
I
That also sounds a little off. from what I-
I did mine.
If I multiply it,
8. So it should be 8. Let's just do it in pieces here. Let's go 18 times 2.44 squared. Yeah, don't forget the square on this. Okay, divided by 12. I got 8.93. What should the units on moment of inertia be? Kilograms meters squared is correct. Now I will add this last piece of the puzzle so we don't run out of time entirely. I do want to finish this absolutely today so we can work on something else tomorrow. A lot of the equations that we will create in the back half of this chapter are analogous to stuff that you already know. So sometimes it can make it easier if you just use what you already know and kind of compare over. In this case, it's Newton's second law. We have been saying that for problems, sum of forces equal to 0. Well, you kind of already know the background of this. What is it actually equal to? Mass times acceleration. And so we would say it's equal to 0 if, what's the case? Acceleration is 0. Right. So here is arguably now your new equation. What would this be for rotation? Sum of torques equals what is the analogous of mass? This is the equation I think some of you were trying to give me earlier for the definition of moment of inertia. What is the analogous for mass? Well, mass is inertia right here, so this is moment of inertia. And instead of acceleration, we have... So in this problem where the person just stepped their foot off, you told me a minute ago that the person is going to rotate. What you should really say, in all actuality, is that they're going to angularly accelerate, and I should now be able to ask you how much they angularly accelerate. Because when you look at this problem, even though there are 3 forces left, how many of them are actually causing torque? 1. So right here, here's how I would solve for the angular acceleration of the bridge. This would be negative torque of victim, negative because it's spinning that way, is equal to, if we had not already calculated I would tell you put in 1/12 ml squared here, but we already know what I is, so let's leave it alone, and we're trying to find angular acceleration. This would be negative lever arm of V times force of V divided by I gives me angular acceleration. Let me finish this real quick. What is the lever arm to the victim?
4.
That was 4 feet, but 1.22 meters. Okay, this is why I wanted you to do those conversions earlier. What was the force of victim? 670, right? Okay, and divide by, we just calculated what is the moment of inertia? 8.93 what? And this should end up, I believe, at about negative 91 and change. And what would the units on this be? Radians per second squared. To show that really quickly, let's see units real quick. A Newton is actually a what? What are the units of a Newton technically? So if I multiply by meters, this would be squared, and then I would divide by kilograms meters squared, which would cancel, 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 and you'd be left with 1/second squared. Remembering that radians is a placeholder, those are the exact same units. Thank you guys for your attention.